Hello, friends. Welcome to the ultimate AP Precalculus lesson before the AP test. This is the last lesson in Unit 3, and the AP test only goes up to Unit 3. What is classified as Unit 4 in the AP Precalculus curriculum is not on the test, but it's expected that teachers will at least cover some of that stuff with the time remaining in the year after the AP test. So anyway, we're finishing up trigonometric functions, polar coordinates, and so let's get on with it. Uh, We're familiar with the idea of rates of change, finding extrema, right, maxima, minima, etc. in rectangular coordinates. It's pretty obvious in rectangular coordinates. We can look and just see like, oh, it's going up, it's going down, etc. But now that we're in polar coordinates, it's going to be a little bit more confusing. Okay, um, and so uh, if we have some type of function, some type of polar function. It's given the name a signed radius of the function because the r can be positive or negative, right? And we've seen that already in some of these functions where the r ends up going on the other side, right? It's like a negative radius. So on that angle, it just goes to their side across the polar coordinates, etc. And so as we're tracing the graph, the whole idea is, are we getting closer to the origin, right? Or are we getting farther from the origin on the other side? I mean, that's how we think of it in rectangular coordinates as well, but it's a little more confusing as we try to think about it here, right? So the whole idea here is that if you have a function where r, right, it's your um, distance from the origin is positive and yet increasing, so it's getting farther from the origin, right? That would be positive and increasing, or it could be negative and decreasing. So if it's negative, like it's on the other side, and then getting closer to the origin, we would call that increasing. Okay, but if it's positive, right, and it's and decreasing, so positive and getting closer to the origin, we would say it's decreasing. And then if it's negative and increasing, so it's negative on the other side, and but increasing, so that means it's getting higher overall in value from negative to positive, then that means the distance between r and the origin is decreasing. Again, confusing, but here's what I'd recommend. That when you see something like this, that you draw out the rectangular coordinate graph, because it's just easier to conceptualize that way. Um, One of the things that you want to be able to do anyway is to be able to go back and forth between models. Good problem solvers do that. They have one kind of model, one kind of graph, a table, something like that, and they can translate back and forth from one to the other. If you're in polar coordinates and it's confusing, you're supposed to be able to go to the rectangular coordinates and use those to help you think about that, right? Or create a table of values. Use that to help you think through the problems. So here's an example of a graph. It's like what we've seen before. And we're going to fill in the intervals where f is positive or negative and increasing or decreasing. So we can see here that here it's positive and increasing. And then it's negative and decreasing, or positive and decreasing to here. Positive just means above zero, and decreasing just means going up or going down. Right? If you were on a roller coaster, are you looking up or are you looking down? That's all it means, increasing or decreasing. But here's where it switches to negative and decreasing, right? So 7 pi over 6 down to 3 pi over 2. So negative and decreasing, and now it's negative and increasing up to 11 pi over 6, but then it switches from negative to positive. And so that's the other interval here where it's positive and increasing. And so in the polar coordinate system, this graph becomes f of theta equals 1 plus 2 sine theta, as shown in the table. And then we've got labels, points labeled A, B, C, and D correspond to the intervals found in example 1. Okay, and so again, we can write this in polar coordinates, but we can think about it from the rectangular graph. Okay, and so it has the same intervals where it's positive and increasing, positive and decreasing, negative, positive, increasing, decreasing, etc. So we can use this. So even if we're presented with something like this, the polar coordinates, the polar function, we can think about it in terms of the rectangular function. Let's take a look at example 2. It says, consider the graph of the polar function r equals f theta, where f theta is 2 minus 4 cosine theta in the polar coordinate system. Which of the following statements is true about the distance between the point with polar coordinates uh, f theta and the origin? Right. So in other words, is the function getting closer to or negative or farther from the origin, etc.? What I'm going to want to do right away, polar coordinates, I'm not used to working a lot in polar coordinates. We do use them at various times, but for this kind of thing, I'm going to want to revert to the rectangular coordinates because I know that I can think better in terms of that. So I'm going to create a little graph of this. So 2 minus 4 cosine x. What I know about this function is that it has a midline of 2 and it's got an amplitude of 4. So it's going to go from 2 up to 6 and down to -2. It's a cosine graph. So it's going to start at the maximum, or in this case, the minimum, because it's reversed. So it's going to look like this. Okay, where this is 2 pi. There are no horizontal shifts or anything like that, no phase angle. This is pi, etc. And so let's take a look. The distance is increased. So in terms of distance from the origin, we can just think of that in terms of distance from the horizontal axis, right? The distance is increasing for theta to 5 pi over 3. So from pi to 5 pi over 3. So that would probably be from here to here, because it's positive and increasing. It is positive, but it's not increasing, right? So the distance between the function and the origin here is actually decreasing. So A is out. B, the distance from 5 pi over 3 to 2 pi is increasing because it's negative and increasing on the interval. So it is negative, but it's not increasing. It's negative and it's going down, which we call decreasing in this case. Okay. C says the distance is decreasing for pi to 5 pi over 3. That's true. It is decreasing, right? We're getting closer to the x-axis because it's positive and decreasing. That's true. Okay, it's positive and going down. And so it looks like C is going to be our right answer. But let's check out D also, just for the sake of being thorough. It says that the distance between 5 pi over 3 and 2 pi is decreasing, and that's wrong. It's not decreasing. The distance is actually increasing. So that's example 2. Example 3. So here we have another graph. It's shown, and they give us the function. Now, we're going to translate this to polar coordinates, where f of theta is 3 sine of 2 theta, and r equals f theta. It's graphed in a polar coordinate system for 0 to 3 pi over 2. And so that would be like a cycle and a half, right? So 1.5 periods of this. It says, on which of the following intervals is the distance between the point with the polar coordinates and the origin decreasing? Right? So again, uh, we're looking to see where is it getting closer to the x-axis in this case. And so from 0 to pi over 4, 0 to pi over 4, it's getting farther from the x-axis, which means that in the polar coordinates, it would be getting farther from r, or farther from the origin, I should say. Pi over 3, pi over 2 to 3 pi over 4, nope, it's getting farther away, right? Getting farther from the x-axis, which would mean that in the polar coordinates, it's getting farther from the origin as we trace out that line. 3 pi over 4, yes, here we're getting closer to the x-axis, so it looks like that's going to be our answer, but let's check out D just in case. And it's from pi to 5 pi over 4. That's getting farther away. So our answer is C. Another characteristic of functions and graphs that we've looked at is the extrema, right? Maxima and minima. And the same thing applies. Same way we were talking about increasing and decreasing in the polar coordinates. Well, the same thing in polar coordinates, there can be extrema, maxima, and minima. And probably the best way to think about this, again, is to translate from the polar to the rectangular coordinates and look at the graph that way. Okay, so example 4 says consider the graph with a polar function 1 minus 2 sine of 2 theta in the polar coordinate system for 0 to pi. So because it's got 2 theta in there, we're shrinking the period. So it's just pi. It's a sine function. So why don't we draw this and take a look. Okay, I know this has a midline of +1, but it has an amplitude of 2. So this is going to be -1, 1, and it's going to go up to 3. And I know that 2 theta, so it's a negative sine graph. So sine starts at the origin, so it starts at the midline at least, and normally would go up, but it's got a -2, which means it's going to go down. When it gets back to the midline, and this point is pi, this is pi over 2, etc. Right? And then it's crossing here when sine is 1/2. So those points are going to be, when does sine equals 1/2? At pi over 6. So this is going to be right here. That'll be pi over 12. And then also at 5 pi over 6. So this is going to be 5 pi over 12. One more pi over 12, and we're at 6 pi over 12, which is just pi over 2. This is what we expect to get. Okay, so anyway, now we've got this graph. We can use this to help us answer this question about where we have maxima and minima. So the graph of R has a relative minimum on the interval pi over 3 to 2 pi over 3. So let's see, pi over 3 and 2. So pi over 3, where is that going to be? Well, we know that this is pi over 4. Right, again, just fill in the numbers here. So this is pi over 4. And here, this is 3 pi over 4. Pi over 3 is going to be in here. Right? And then the other one they're talking about is 2 pi over 3. That's going to be over here between pi. So there's no relative maxima there. So A is out. B says between 2 pi over 3 and pi, because R changes from decreasing to increasing. So let's look at 2 pi over 3. Yeah, okay, to pi. So here's 2 pi over 3. Here's pi. Okay, there is an extremum there, a maximum to be particular. It says because it changes from decreasing to increasing. That's not right. Here it changes from increasing to decreasing. So B is out because of the reasoning behind it. C, the graph has a relative maximum on the interval pi over 3 to 2 pi over 3. We already saw there's no extremum on that interval, so C is out. All right, it has a relative maximum from 2 pi over 3 to pi, so that's the same as B, except it says changing from increasing to decreasing, which is what we said before, and so D is the right answer to example 4. Another concept that came up in our other lessons is the average rate of change. Right? And so even in a polar function, we can have an average rate of change. We're just taking everything we did before and applying it now to polar functions. Right? So it's great. Everything was hard before, and now it's all just moving in a circle. Right? But again, what you can do is go back, refer everything back to the rectangular coordinates the way you understand it there. Average rate of change works the same way, right? F of B minus F of A over B minus A. You can think of that as, rise over run. If you just connect the 2 points, the line there, what's the slope of that line? And so here is a polar function that they give us in the polar coordinate system. What is the average rate of change over the interval pi over 2 to pi? So we just plug the numbers in, and we're going to see how this turns out. So our function, so it's going to be f of B minus F of A over B minus A. Okay, so we're going to have 3 minus 3 cosine of pi minus 3 minus 3 cosine of pi over 2 over pi minus pi over 2. And as we as we solve this. So we know that cosine of pi is -1. And we know that cosine of pi over 2 is 0. So that whole term disappears, and we end up with a 0 there. So we end up with 3 minus 3 times -1. I'll put that in there. Minus 3. And then there's just that 0 there. Pi minus pi over 2 is going to be pi over 2. Simplify further. So I'm going to do all of this here now. So 3, -3 minus -1. So this is 6. So 6 minus 3 is 3. 3 over pi over 2. I end up with 6 over pi. Okay, so that is the average rate of change for the polar function on that interval. Example 6. Here they give us a particular function, and they give us the graph of it, the polar graph. And we want to know on which of the following intervals is the average rate of change equal to 0. Well, one thing we could do is to just go back and look at the rectangular coordinates and look at it there. Average rate of change equals 0, though. What would that mean? What it means is that when you connect the 2 points, there's a horizontal line between them in rectangular coordinates. Basically, f of theta is the same for both ends of the interval. Let's draw it out. So here we've got the graph. It has a maximum of 3, minimum of -3, and then the period is just pi. So let's take a look at these intervals now. So pi over 4 would be here, and then 3 pi over 4 would be here. Okay, if we connect these 2 points, we do not end up with a horizontal line where the slope is 0. Now 3 pi over 4 is here, and 5 pi over 4 is here. Again, if we connect these 2 points, we do not end up with the slope of 0. So then 3 pi over 4, again here, and 7 pi over 4. Okay, now that's over here. I didn't draw it well, but these should be at the same, both at the minimum, and so it would be a horizontal line between those. So that should be the right answer. And then D, let's just see this one to be sure. Pi over 4, so that's here, and 7 pi over 4, that would be here, right? And so again, connecting those 2 points would not be. What does this look like on the polar graph, though? Since we have the polar graph, let's take a look. So where is 3 pi over 4? Let's mark this point. 3 pi over 4 is here. It's just the angle, right? Angle going around this way, we get to 3 pi over 4 like that. There's 3 pi over 4. 7 pi over 4 is over here. And so then if I trace the r around from here to here, notice I'm staying at the same point, right? I'm just staying at the same r the whole time I go around. It's neither increasing nor decreasing, right? The value of r, the value of f theta is not increasing or decreasing. It's staying the same. So the rate of change is 0 for that. In example 7, we're given a graph of a polar function, and we're not given what the function is. We're told simply that it passes, from A through B, C, D. So it's going around the way a polar function is normally graphed. And there are no holes, no asymptotes or anything like that, right? Passes through all these labeled points in that order. So now we want to know on which of the following intervals is the rate of change the least. Okay, well, let's think about this. Going from A to B, at A and B, R is the same value. And so here the rate of change from A to B is 0. From B to C, R is increasing. Right? And so this is an increasing rate of change from B to C. So that's out because that's definitely more than what it was from A to B. C and D are both the same R value. And so that's 0. So it looks like it might be A to B and C to D. They're both 0 rate of change. But D to A is decreasing. R is decreasing. So this would be a negative rate of change. In other words, a decreasing rate of change. And so that is the least rate of change. So that's the answer D. Just like we had in rectangular coordinates, point slope form. Well, we can think about this the same way, where, but again, the slope is the rate of change, right, or the average rate of change. And so, because of the way that our polar coordinates work, this is going to give us something approximate. If it's a linear function, that's great, but may not have that um, direct proportion kind of relationship. So what we can do is we can use um, rates of change and particular points to estimate what the points are, right? So here's the point slope form. You may or may not remember this: y minus y1, m times x minus x1, right? So x1 and y1 are a known point, and m is the slope of the line. Well, slope in this case is, f of b minus f of a over b minus a. The y coordinate, what we would call the y coordinate, is the f, right? So that's our y1. Here's y, just y, right? So it's flipped over there. And then x minus x1, or theta theta minus theta1, that's like x minus x1, right? That's the independent variable we're putting in. It's the input in the function. And so we can estimate what f theta is going to be based on this formula that we have here, which is analogous to the point slope form, just in a different set of coordinates. We're going to see that here in example 8. We're going to apply this formula using the table of values that they've given us here. So we've got 2 points. These 2 points are what are going to go in here, but we need a reference point as well. And so our reference point we're going to use is pi over 6. You could use the other one, but this one comes first, smaller value. So we'll just use this one. And so we're trying to find f of 5 pi over 6. So f of 5 pi over 6 equals f of theta 1. So that again is our pi over 6 plus. So now it's f of b. So it's 7 pi over 6 minus f of pi over 6 over, and now it's just the thetas, right? Theta 2 minus theta 1. So it's not a 2. 7 pi over 6 minus pi over 6 times, and then um, our reference, sorry, times the theta that we want to put in, our input, right? So 5 pi over 6 minus our reference point, which is pi over 6, our reference theta. Now we're going to simplify, or plug in and simplify. So f of pi over 6 is 2. So it's going to be 2 plus, and then at the top here, it's -1 minus 2, right? 7 pi over 6 is -1 minus, and then f of pi over 6 is 2, divided by 7 pi over 6 minus pi over 6 is just pi, times, again, 5 pi over 6 minus pi over 6 is 4 pi over 6, or 2 pi divided by 3. So let's see how this simplifies. So I'm going to 2 plus, and on top here is going to be -3, right? This is -3, but that cancels out with this guy down here. The pi cancels out. So I'm just left with -2. So 2 plus -2 equals 0. So we're approximating that the point, that f of 5 pi over 6 is going to be about 0. So again, a lot of application, a lot of stuff we've learned before, just applying it to polar coordinates and seeing that all these rules we've learned before, they still work. And don't forget this idea of being able to switch back and forth from one model to the next. It's a mathematical skill, but it's really to help you understand, to be able to help you think through what these problems are. So thanks for watching. Don't forget to like and subscribe. And good luck on the AP test.